Okay, we are on electronics worksheet 24.2, question number 5. Part A, state the name of the gate and draw its truth table. So this is quite easy. You can see this dot here means that there's a NOT gate connected to it, right? And this fish shaped looking thing tells us that it's OR. So OR with NOT becomes a NOR gate. Alright, how do we draw the truth table? So before I start, let's look. How many inputs are there? 1, which is Q, and 2. This is P. So since there are 2 inputs, I need to have 2 to the power of n, right? Where n is 2. So 4 rows. So 1, 2, 3, 4. I'm going to draw one more so that I have my heading. So this is P. This is input Q. Now, remember I told you that when you have a NOR gate or NAND gate, always do one part first. I'll do the OR first, then I'll do the NOT. Okay, so this is going to be our final answer. So our final answer will be this part here. Alright, so alright, so let's start. We start with 0, 0, 1, 1, 0, 1, 0, 1. This is our usual standard table, right? Standard truth table for any 2 inputs. So starting with OR. So 0, either one must be high in order for the output to be high. So this is going to be low. There's 1 high, so output high. There is 1 high here, so output is going to be high. And there's at least 1 high here, so definitely output is going to be high. Then we're going to invert or inverse our result. So since this is low, it's going to be high. And this is high, so be low, low, low. So this is our answer. Now part B, state and explain the logic level at input P when the temperature is high. So I want to state and explain logic level at P when temperature is high. Now let's take a look at this. What did they tell us? In the question they tell us that they just tell us that this circuit is used to activate one of the many water pumps to a large pond, right? So now P, we're talking about P. So when the temperature is high, so what am I concerned about? I'm concerned about this thing here. What is this device here called? What is this component here called? It's called a thermistor. So when temperature of the thermistor is high, you know that resistance of the thermistor will decrease. When resistance of the thermistor decrease, the potential difference across the thermistor will also decrease. Now take a look. Over here is 6 volts, right? How do I know 6 volts? Because it's connected to this 6 volts side. And on this side here, this is going to be 0 volts. So when the temperature increases, it leads to the potential difference across the thermistor dropping. This tells us that over here we'll have a low potential. Now if it's a low potential means my input here is going to be 0. So what's the logic level at input P? Logic level will be 0. How do I explain why? You will explain using all this, telling us that because of the temperature, when the temperature is high, resistance of the thermistor will decrease. When the resistance of the thermistor decrease, the potential difference across the thermistor will decrease. And so since the potential decreases, it results in a lower potential at point P. So the logic level will be 0. Next, state and explain logic level at input Q. So logic level at Q when both contacts are below the water level. Now let's take a look. When both contacts are below water level, let's erase all this first, okay? So when both contacts are below water level, this tells me that, now over here initially 6 volts, right? And over here would be 0 volts. So if it's underwater, it means that your water will be something like this, above this height. and it causes the resistance between the contacts to decrease. Why is that so? Because you talk about pond water, it's not pure water, therefore it can conduct electricity, isn't it? If it's in air, then obviously it's an open circuit, so current cannot flow. But now that there's water, current can flow. So I'm going to say that at this point here, it is about 6 volts. Maybe slightly lesser, but it doesn't matter. Let's assume it to be 6 volts. So since it's 6 volts, means it's going to be at a high potential. So I'll call this logic level 1. So the logic level will be 1. Why is that so? Because when it's underwater, resistance is low, current can flow. Now let's go to D. Hence, state the necessary conditions that will activate the water pump. Now, what do you want? When do you want the water pump to be activated? You want the water pump to be activated when there is low water, right? When the water level is low, because if the water level is low, your fishes are going to die. So you wanna make sure that the water pump is activated when water levels are here low. So when it's low means over here should be 0. Let's change that. Okay, so we want the water level to be 0, and you want the temperature to be high, because when temperature is high, it means that, you know, maybe your water is evaporating or the water is getting hotter, and you don't want the water to be too hot, otherwise the fishes will die also. So you want to add water to it. Just now we said that when temperature is high, the logic level will be 0, and when both contacts are below the water level, it's 1. So actually what the conditions required would be 0, 0. Right, so we want this side to be also to be low. And what gate is this? This is a NOR gate, right? So if you look at our table over here in part A, we want P to be low, we also want Q to be low in order for our output to be high. There we go, for our water pump to be activated. So what we have guessed is correct, or what we have said is correct. Necessary conditions, we want the water level to be below the contacts, and we want temperature to be